the recording. Um, so before the break, before the exam, we are discussing about bipolar junction transistors. I'll just quickly go through it. All of you now know the construction of a bipolar junction transistor. So we have a N region. So basically, um, uh, so for a NPN bipolar junction transistor, so emitter is made of N-type semiconductor, base is made of P-type semiconductor, and collector is made of N-type semiconductor. And we had done this exercise before. So if the emitter doping is Ne, so there are Ne number of electrons and Ni square by Ne number of holes, right? Similarly, if there are Nb, the doping of base is Nb, so I have Nb number of holes and Ni square Nb number of electrons. If there are the collector doping is Nc, in collector I have Nc number of electrons and Ni square by Nc number of holes, right? This is at room temperature. Okay, so we also looked at the operation. So basically, we looked at two modes of operation. So three modes of operation. One is cutoff. So when generally in a bipolar junction transistor, your base emitter junction is a emitter input port. So either you have to forward bias the base emitter junction or reverse bias the base emitter junction. So we tell, okay, transistor is on when base emitter junction is forward biased, right? And your output port is your collector and base junction. Basically, so you always means give your take your output either from collector or emitter. So uh, so uh, so in the normal operation, if the collector base junction is, let's say your base emitter junction is forward biased, if the collector base junction is also forward biased, then we call it the saturation mode of operation. That means we're putting a lot of electrons to the base and base is saturated with electrons. Uh, if collector base, the emitter base junction is forward biased and collector base junction is reverse biased, we call it the forward active mode of operation. That is the most traditional way your bipolar junction transistor works, when the collector base junction is reverse biased and emitter base junction is forward biased. So just to note down, so we had cutoff, right? Cutoff mode of a cutoff region. So basically, when the base emitter junction is not forward biased, right? So basically, uh, uh, so this is cutoff, and we have saturation when the both the junctions are forward biased, and we have forward active, right? Forward active when emitter base junction is forward biased and collector base junction is reverse biased. So here in this schematic, so this is so I have given VB. So your emitter base junction is forward biased and collector base junction is reverse biased, because VC is greater than VB, right? So if collector voltage is more than base voltage, that means collector base junction is reverse biased, right? And so we know the operation of bipolar junction transistors. So the moment emitter base junction is forward biased, we are injecting electrons from emitter to base, and holes from base to emitter. But in this case, we had made your emitter very highly doped so that the injection of holes from base to emitter is very low, right? So, so, uh, the operation is, so basically we inject your electrons from emitter to base, right? We inject electrons and these electrons diffuse in the base, and the moment they reach the base collector junction, they're collected, right? So there is a very high electric field and they're collected, right? So we also looked at different components, current components. So I have so emitter current has two components. One is electron injected from emitter to base. There are hole injected from base to emitter. So I have this IEN and IEP, the current because of electrons and current because of holes. Similarly, some of the electrons injected from emitter to base are collected. So the collector current has also two components. So one is ICN. ICN is the ICN is the electrons collected by the collector, right? So part of IEN right, is collected. So the ICN is part of IEN. And ICO, because this junction is reverse biased, right? Collector based junction is reverse biased. So reverse biased junction also has a very high electric field here, right? So this is the electric field across collector based junction. So the minority carriers, right? So here in this case, if you look at the collector and base, right? Uh, right. So let's say base and collector. I have holes here, minority holes here, and I have minority electrons in the base side, and I have electric field in this direction, right? So the minority holes can drift from collector to base, and minority electrons can drift from emitter to base to collector, right? So this ICO is because of that. ICO is because of this drift of minority carriers across the junction. So IC has two components. One is ICN and ICO. And basically, in general mode of operation, your ICO is very less. So IC is mostly equal to ICN, right? Okay. Then the base current has three components, right? So one is IP. So we are injecting your holes from base to emitter. So that will be part of your base current, right? IP. And also, since the electrons are traveling from emitter based junction to collector based junction, so they also get recombined. So that is the your recombination current IBR. And also this ICO component, as I told you, right? So your minority carriers also drifts across the junction, and that is that part will also come in the base, right? So the base has three components, and generally, if you neglect ICO is very less in the normal operation. So that will have two components, IP plus IBR, right? And we want our current gain. So this is the alpha. Alpha is your common base current gain. So alpha, you want my alpha to be 1, IC by IE to be 1, and the beta, which is the common emitter current gain, right? So beta is the common emitter current gain, which is alpha by 1 minus alpha, should need to be very high, right? So so I could also write this alpha by IC by ICN times ICN by IEN times IEN by IE. So this IC by ICN, this is because, see, if you look at IC by IC, um, so if I do that, so let's say here, so if I do IC by ICN, right, this is nothing but 1 plus ICO by ICN, right? So ICO by ICN is means generally we want it to be less, right? ICO, but we also saw, right, in the because this junction is reverse biased. So as you go on increasing the reverse bias, that might be a possibility of multiplication, avalanche multiplication, and all those things. We'll come back to it later. So uh, okay, so this is IC by ICN is your multiplication term here, right? And in general operation, this is 1, right? So because we don't means IC by ICN, so you see in the general term, IC by ICN equal 1 plus ICO by ICN, and this part is neglected. If this part is neglected, then this will be 1, right? Then ICN by IN, this is my base transport factor because I'm injecting electrons. So how many electrons reach the collector base junction? So that is my base transport factor. And then the emitter injection efficiency gamma. Gamma is, so IE has two components, IEN and IP, right? And I want my gamma because this is my emitter injection efficiency, which is nothing but IN by divided by IN plus IP, right? So if you want your alpha to be equal to 1, then your base transport factor and your gamma should also be very close to 1, right? That means your ICN should be equal to IN. That means your IBR is less than IBR, your recombination time equal to 0, recombination current equal to 0, because you see, if I want ICN equal to IN, right? So that means this is the base, all the electrons you are injecting from the emitter base junction is arriving in the collector base junction, that means there is no recombination, right? Or and for the higher injection efficiency, your IN should be equal to IE. That means your IP you should design in such a that IP equal to 0, right? So these are the two device design conditions, because you want your alpha to be 1. So the first condition is you have to make sure that there is very less recombination, or there is very less injection from base to emitter, right? So we have also derived this currents, right? We derived the IEN. So I have taken this from my earlier note, this page here. So your IEN we have derived. So IEN equal to QNI square AEDN and divided by NB TB dash times exponential VB by VT minus 1. So here you see this is the emitter area, right? Emitter, this is junction area of the emitter base junction, right? And that is the area of your bipolar junction transistor, right? So if you want to see current density, then you have to divide all the currents by this emitter area, right? Emitter area is means the area of your area of the transistor. Okay, so we had also derived IP, IBR. So base recombination current, current injected from, means current because of holes injected from base to emitter. So this part we have derived. And as I also told you, right, see this part NB and TB dash, because here we have, while deriving these equations, we have taken that your doping in the base is constant, right? Doping in the emitter is constant, doping in the collector is constant, but that may not be true in the real devices, right? So so this then I have to write down, because your NB, the base doping is also varying. So this is NX DX 0 to TB dash, right? So this part is nothing but your Gommel number, right? And basically your Gommel number in when you're modeling, because your base doping is not constant. So so this the denominator is nothing but you just I mean put it in the Gommel number term, right? Base Gommel number, right? And similarly, IP also has this is because of hole injected from base to emitter. So this has a Gommel number of electron. Sorry, the emitter Gommel number, right? Um, So, okay, and IBR is the base recombination time. So this is the equation where I have this tau. Tau is the minority carrier lifetime in the base. If the electrons are injected to the base, how long they could survive in the base. That is the minority carrier lifetime, right? Okay. So, and if you want gamma to be 1, then IEP should be as low as possible. So your IEP should be much lesser than IN. And we had done this, right? So IP by IN is nothing but dP by dN times NB by NE times TB dash by T, right? So if I want, means I want my IP to be much less than IN, right? So that means my NE should be higher than NB, right? And your emitter length of the emitter, I mean, it should be thickness of the emitter should be more than thickness of the base, right? So these are the design thing, because that's the reason we make your emitter highly doped, right? We make our emitter needs to be, emitter is doped higher than base, right? Higher than base, right? This is the reason, right? And also we want the thickness of the emitter should be much higher than thickness of the base. And for that, I also told you, right? We have to go to the polysilicon emitter, right? I will also discuss briefly what is a polysilicon emitter, right? Okay. All right. So now, so this is about emitter injection efficiency that we had discussed. And then the base transport factor alpha T is ICN by IN. So you could write ICN by IN minus IBR. So by IN. So I could write alpha T is nothing but 1 minus IBR by IEN. So if I do the math, then it will be 1 minus TB square by 2 tau and DN, right? And basically what I want my base recombination current, I want need to be very low, right? It needs to be very low, right? Because when you're designing a bipolar junction transistor, you have to make sure that your base recombination time is very less. So that is possible. Use your TB dash should be low. Your neutral base width should be low. So if the neutral base width is low, that means the injected electrons are not spending a lot of time in the base. So there is a less possibility of recombination. And anyway, your tau n should be high because so tau n should be high means your recombination lifetime, right? So your lifetime of electrons, minority carrier lifetime should be very high. So for that, that means your base should have very less number of defects, right? Base uh, should have very less number of defects. It should be a very less number of defects, right? When I talk about defects, defects are crystal defects or impurity induced defects, right? So your base should be defect free. If this is defect free, then the minority current lifetime will be very high and your recombination current will be low, right? And your DN, so your this is your diffusion length should also be high, and diffusion length depends on the means how far the electrons could travel without recombination, means diffusion length, right? So so for the diffusion length to be high, your doping should be low, right? If even that has a doping dependence, right? Diffusion length, right? So your doping should not be very high in base, right? So if the doping is very high, then the DN will be low, right? So then you will have issue, right? So your base doping cannot be very high. Okay, so so this is about the base transfer factor. We had already discussed this. This is just for to remind whatever we had done before the mid semester exam, right? Okay, so now I talked about, right, we should have a polysilicon emitter because we want, so this is your thickness of the, this is the thickness of the emitter, and this is the thickness of the base, and this is the thickness of the collector, right? So as we saw, if I want higher injection efficiency, my thickness of the emitter should be high. So so basically T should be more than TB, right? Thickness of the emitter should be higher than TB. So if you so what means, basically that is desirable, right? This is desirable for higher injection efficiency. But the point is, if I want to do it in the implantation method, because if you see how do you form the base, so you have your collector, right? Your collector is n-doped, right? So let's say your collector is here is n-doped collector. So you will implant your base, right? Your base, then you will implant your emitter, right? So if I want this TE to be deep enough, TE to be higher, that means your, see, implantation is generally done by the implanters, right? And basically if you want TE thickness to be high, right, this TE to be high, then your implant energy needs to be high, right? And also the base comes below T, below emitter, right? So when you form the base, then the base, implantation energy for the base implant is much higher than the, should be higher than the implantation energy for the emitter implant, right? But even for the thicker emitter, the implantation energy for the emitter implant is high. So the implantation energy for base implant will be even higher, right? So with very high energy implanters, it is very difficult to control the base width because TB, see, the parameter, the your bipolar junction transistor parameter depends on the base width, right? Base thickness, right? If the base, there is little bit change in the base thickness, there will be a lot of change in the characteristic, in the Gammel plot, or in the characteristics, right? So you want your base thickness to be properly maintained, right? So for that, you don't need it to be followed by very high energy implanters, because high energy implantation means when you do high energy implantation, it is difficult to control it, right? So it is difficult to control the depth of the base. So what is generally done is, uh, we I just copy this part. So what is generally done is, we reduce the anyway. So we start with lesser implant, lesser emitter thickness here. Let's say, right, and it is very easy. Now this emitter thickness is low, so it is very easy to control the base width by implantation, right? But on top of that, we deposit poly, right? So the emitter thickness is increased by this polysilicon, right? So this is, so basically what happens. Um, okay, so this is my polysilicon, right? And this is end of polysilicon, right? End of polysilicon. The so right, and if you see, so this part here, this is part here also endowed here, right? But since this is polysilicon, so, and I could, so once I, so this can be done afterwards, right? This can be done after your base is formed, right? After your base is formed, right? And since this is a deposition process, right? Since you are depositing polysilicon is deposited on top of silicon, right? Since this is a deposition process, the thickness uh, can be managed very well, right? Thickness can be managed very well because this is a deposition process, right? So this is managed very well. So this is called polysilicon emitter, and polysilicon emitters are very widely used nowadays because most of the modern bipolar junction transistors are made with polysilicon emitters, right? Emitters are polysilicon, not monosilicon, right? Monocrystalline silicon. So since this is done by deposition, I could by changing means by I could easily, means basically by changing the deposition time, I could easily change the thickness of the emitter, and I could control the emitter, means injection efficiency very well, right? All right. So this is polysilicon emitter case. Then also there is another thing which I need to discuss before we move ahead. Um, is something called emitter crowding, right? So since you are doing simulation, you might have observed emitter crowding effect. I'll write down here emitter crowding, right? So let's take. So this is my my bipolar junction transistor. The schematic I have shown, right? So I have my emitter, base, and collector NPN. Let's say your base emitter junction is forward biased. That means I have connected this to ground here, and I give a positive voltage VB here, and I give a VC, right? Okay, so this is operating the productive mode, right? So this junction is now forward biased, right? Emitter based junction is forward biased. This is my emitter based junction, which is forward biased, right? So electrons are injected, right? So the but the if you see, uh, there is a whole current, right? So there is, see, there is a base current, and what is the base current? So base current, the what is the direction of the base current? So base current is in, right? So basically this is the direction of the base current, right? So let's say this is the direction of the base current, right? right? So base current is always going in, right? Collector current is also for NPN transistor. Base current is going in, collector current is going in. Only the emitter current goes out, right? Right? Okay. So if the base collector is going in, so I have a finite resistance because you see my base width is not also very base thickness, right? So this is my base thickness, right? This is my base thickness, right? So TB is low, base thickness is low. The base doping, yeah, just a moment. So your base doping NB is moderate, right? So this is not very high, not very low, right? So if you look at the base resistance, if you look at the base resistance, resistance of the base region, right? The resistance of the base region is high, right? Resistance of the base region is high, right? Okay. So as you are, I mean, see, if the base current is going in, then there is a base resistance here, RB, right? So if I'm giving zero point 0.7 volt here, so there is a voltage drop, right? So the voltage reaching the emitter base, because your emitter base junction need to forward bias, right? So if you're applying zero point 0.7 volt, let me do it properly. So let's say this is the resistance, right? Um, Let me remove this part here, right? So let's say this is my the resistance of the emitter base means emitter base junction, so base resistance RB, right? So if I'm applying zero point 0.7 volt here, right? So if I go in the, means in this direction, the voltage means voltage is nothing but your applied voltage minus IB times RB, right? Applied voltage minus IB times RB. So if I'm applying zero point 0.7 volt here, the voltage reaching here might be zero point 0.7 volt at this point. The voltage reaching here might be zero point 0.5 volt. Voltage reaching here might be zero point 0.4 volt, right? So there is a continuous drop from the base contact to your emitter. So there is a voltage drop, right? So if you see the emitter here, so the sides of the emitter, right? So here this part is biased, right? At a higher voltage compared to the middle of the emitter, right? So if I see, you could I will draw again. So this is my, let's say this is my emitter, right? And I have my base contact here. This is my, let's say this is my base, right? This is p-type base, right? And this is n-type collector, right? So I have a finite resistance, right, between base and emitter, right? Because, right? So if I'm applying 0.7 volt here, that means there is a drop, right? And this is means drop at every point is like zero point 0.7 volt minus IB times RB, right? So there is a gradient, right? So basically, if I have 0.6 volt here at this point might be 0.55 volt, this point may be zero point 0.5 volt, this point may be zero point 0.4 volt, right? This is how there is a voltage gradient because your voltage minus IVRB because current direction is also like this, right? Okay. So if you see here, so at the side of the base emitter junction, at this point, side of the base emitter junction is forward biased by zero point 0.7 volt, but the middle is forward biased by zero point 0.4 volt, right? That means the middle of the emitter, this part, right? This part is less forward biased compared to the side, right? Right? So the more, because this part is highly forward biased, heavily forward biased because zero point 0.6 volt on the middle is only zero point 0.4 volt in this example. That means most of the current will flow at the edges, right? So most of the current, right, will flow at the edges, right? Because this part is for this basically uh, uh, this part is heavily for the side of the emitter is heavily forward biased, right? So the current I am talking, when I am talking about current, the current will mainly from is flow at the side, right? So this is called emitter crowding. That means even if your emitter area is big, right? So you have emitter area, right? You have emitter area, but most of the current is flowing in this region and in this region, right? So right. Uh, so basically that means the the current is crowded only at a very even if you have a large emitter area AE, but the currents are only crowded at the corners, right? This is called crowding effect, emitter crowding effect, right? So what happens in emitter crowding effect, because lot of current flows as a very small area, so it increases the heating at this part, right? So this is one of the thing. But the point is, but you're not utilizing the full emitter area, right? So and you see this is many times it is called the hollow emitter. The emitter is hollow because the conduction is only happening at the periphery, right? Conduction, if you look at the emitter area, the conduction, if you look from the top, right, let's say this is my emitter, the conduction is only happening at the sides, right, and the in the middle, right, there is no, because this is not properly fertilized, so there is no conduction happening, right? So this part of this area is wasted, right? This area is not utilized properly, right? This part where the conduction is not happening, right? So this is called hollow emitter or emitter crowding. So this is okay if you are talking about very low current, but when you are designing a power amplifier, or you need to design some circuits where the current drive strength is very high, right? You need very high current from your bipolar junction transistor. So there it will create issue, right? So this is emitter crowding effect. Means so I mean this is not very good. And what is generally done is you don't really use big emitters. So what you do is you divide your emitter to smaller regions. So basically what you do is, um, if you have emitter, so basically you see, you create your base also. So basically this is your base, right? So emitter, you make emitter fingers, right? Generally you so to avoid this emitter crowding, you divide emitter into smaller regions and connect them in parallel, right? So if you see, so these are the emitter, right? So let's say these are different fingers, right? Emitter, right? So these are different emitter fingers, and also I have base fingers, right? These are base fingers. These are base fingers here, right? So what I have done is I have divided my bigger emitter, because if you want to handle high current, you need higher emitter area, right? But the moment you have higher emitter area, so you will have emitter crowding effect, right? So what you do is that we divide this higher emitter area to smaller areas. Then you have a multi finger kind of connection, so where emitter and base are very close to each other, right? So in this case, since the area of the emitter has reduced, right, so current crowding will reduce, right? So we have this kind of structure, right? So let's say I have my collector, so I divide my emitter, so this is CB EB, so BEB EEB EB, right? So basically you see what I've done, I have divided this part. If you look at um, this region here, right? So I have divided my emitter into 1, 2, 3, 4, 5 emitters, 1, 2, 3, 4, 5, 6 base, right? So I have divided my emitter and base. So I have done a finger connection, right? So but I have all the emitters are connected together, all the bases are connected together, right? You could think these are parallel transistors connected in parallel, right? But so my current is still the same. My total emitter area is the area of each finger, right? Area of each finger into number of fingers, right? So in this way I could reduce the current crowding effect, because if you see, uh, so this is my base, right? This is my base current, this is my base current, but since the emitter area has reduced, so there, I mean, basically all the regions will be properly biased, right? All the emitter regions will be properly biased, right? And similarly, since right, so you could decide the number of fingers, right? So if your emitter area increases, you could increase the number of fingers. By doing that, you could reduce the current crowding, right? This is very commonly used, means commonly used technique to uh, lay the, means to draw the bipolar junction transistor, lay out the bipolar junction transistor, right? um, and we have, so here you see I have right, but I have this collectors, right? Collectors at the side, right? And I have means I have made the finger side, base emitter finger side. So many cases also I could have um, right, I could also have insert, I can insert a collector in between, so I could have CBEV. So I could also uh, like so let's say, right, so I could have something like this, so right, so here means I have divided also, here I have two fingers, two emitter fingers, here I have two emitters, so total I have four emitter fingers, right? But I have inserted the collector in between, so that collector resistance, because see, the collector also has a finite resistance, right? But collector resistance is not a factor. I mean, it will be a factor when you go to the frequency, means FTF max, F max, right? But in this case, but if you compare this one here, the one means first design and second design. So here I have made emitter fingers and base fingers, and also I have made one collector, right? So extra collector in between, so that collector resistance is not compromised also, right? Right. So these are the traditional means this is how the means you draw the bipolar junction transistor, lay out the bipolar junction transistor to handle very high current, right? So emitter crowding, the emitter crowding is a bigger concern, right? So you see, when your transistor is means conducting more current, right? So transistor is giving more current, right? So your IBRB drop, your IR drop will also be high, right? So emitter crowding effect increases as you draw more and more current of a bipolar junction transistor, right? So for that, to avoid that, you have to make this emitter and base fingers, right? And keep those fingers very close to each other, so that your emitter crowding effect can be reduced, right? Okay, so this is so this is one of the commonly used technique, and this is used widely when you design very high emitter area bipolar junction transistor. You have to digitize your fingers, right? You are digitize your width. So this is called interdigitated fingers, right? Emitter fingers are best fingers. Okay, so any questions here?
Sir, what
Sir,
was the advantage of inserting that extra collector in between?
So that collector current can also, so basically you see here, if I let's say uh, see, every emitter is also means basically you are having collector current, right? Right, right, and let's say these two currents are going down, right? But as you go on increasing the number of fingers here, the collector current is also traveling a longer path, right? So if I'm applying VC here, right, so there will also be drop here, right? So to avoid that, I mean, see, if my number of fingers are very big, right? Number of fingers are large, right? I am dividing large number of fingers. So it is always advisable to insert a collector also in between, right? Those fingers, so that the currents will not be, means your collector resistance can be optimized, right?
Yes, sir, got it.
sir, I had a question. If I am first applying the VC voltage and then I'm slowly increasing my emitter voltage. So when my base emitter junction is not sufficiently forward biased, So my base current would be outside of the transistor. So sir, then my voltage drop would increase inside.
No. Okay, so when the base emitter voltage is less, your current is less, right? So there your IB RB drop will be less, IR drop will be less also, right? Right. So your IR drop. So see, um, let's say this is my this is your emitter, and this is your base, right? Uh, so this is your base contact, right? Let's say this is your base contact here, right? And I have a RB here, right? So there are two contacts, so I'll have two RBs, right? Basically, right? So okay. So now, right, as you go on increasing your base to emitter forward bias, your VBE increases, your IB will increase, right? So your IB RB drop will also increase, right? So when you're handling very low currents, it is not a very big issue, right? Because your IB/RB drop will be less, right? But when you're handling very high current, let's say in some circuits you need very high current, right? That means your emitter area is very large. That means your IB means your means IB also scales with area. All the currents will scale with area, right? Emitter area, right? So your IB is also increasing, right? So higher the IB, this IB/RB drop will be higher, right? So if I'm applying zero point 0.7 volt here, right, and so if I look at this uh, if I look at this emitter, right, so there will be a voltage grading from left side of the emitter to the middle, right, and similarly from the right side of the emitter to the middle, right. So what I'm telling is maybe you will have a grading, right, zero point 0.6 volt at this point, 0.55, even if you are applying 0.7 volt, and there is a grading, right, 0.6, 0.5, 0.4, like this, right. That means this side of the so this side of the emitter is heavily highly forward biased compared to this side. That means more current will flow where it is more forward biased, right? Right. So this is that means your emitter is not uniformly forward biased emitter area. So some part is very highly forward biased, some part is very low forward biased. So the current will crowd in the region where it is heavily forward biased, right? So that means most of the current is flowing in that path, right? So emitter means that is called emitter crowding. So your current crowding takes place only at one region, but the other region is, so even if your emitter area is big, but the only small part of the emitter area is handling the current, other part is not handling current. That means that area is wasted, right? So to take care of that, you could divide your emitter to smaller fingers. In that way, you could uniformly distribute the currents, right? So you could avoid emitter crowding. Uh, did I answer your question? No?
Yes, sir. But I was asking like in the situation where my IB is not flowing inward, it is going outward.
Where IB is going outward?
Sir, like when I was doing my simulation, then I saw
No,
when
IB cannot go cannot outward, right? Then there is something wrong, right? So I mean maybe see, IB has two components. One is recombination component IB and IP. If you have IB and IP only, then your current should go in, right? And if there is something coming, no, you have to look at your simulation, right? Right. So again here, right? Let me go back, right? Right. So you see your IB has three components: IP, IBR, and ICO. Right. If your ICO reverse saturation current is high, your current direction will change. Otherwise, there will be no change in current direction. Right.
yes, sir, it was happening only in the initial voltages when the EB junction was not sufficiently forward
There
biased at
anyway,
very low.
IB is low. IB current is low, right? IB current is low means the potential IBRB will be less, right? IR drop will be less, right? You don't have to worry about when your current is very low,
Yes, sir.
right? But please make sure your IB should go out, right? Sorry, IB should go come in, right? Uh,
Yes,
okay,
sir.
yeah.
Sir, why do we use polysilicon? instead of monosilicon
But when you deposit,
for
you can't really deposit
bandwidth. Yes.
silicon. I mean, so it's very difficult to deposit silicon on top of silicon, right? So when you do the deposition process, means so basically, it's a good question. So uh, let's say if I have already silicon, right? Then when I deposit on top of that, uh, when I deposit, right? So when I deposit silicon, it is very difficult to have the same crystalline form, right? So basically, what happens? It becomes polycrystalline, right? We could still do it. We could do monocrystalline silicon, but then we have to properly control the temperature, and so that called the epitaxy process, right? Epitaxy process is very slow, and the tools are expensive. Epitaxy tools. So what you do is we just do the CVD deposition, right? So you just deposit polysilicon on top of means you deposit silicon on top of silicon. So when you deposit silicon on top of silicon, if you do not do it properly, means not very slowly, then it cannot take the crystalline properties from the substrate, right? That's why it becomes polycrystalline, right? So it is not a monocrystalline silicon, but it's a polycrystalline, right? So right means you have islands, right, of the crystalline island, right? So but that is not an issue because I mean polycrystalline, only thing that polycrystalline silicon will have, they will have more defects, right? So that is good for us, right? So basically but we don't want to do monocrystalline because monocrystalline will be very difficult to grow because we want very thick silicon, right? Uh, Around 100 nanometer, 200 nanometer, we have to grow, right? We have to deposit, right? So there it is very difficult to have monocrystalline silicon growing, right? I mean, means when you deposit, it will be very difficult to have monocrystalline silicon. So that's why it become polycrystalline.
Okay, so
Yeah, we don't intentionally do polycrystalline since when you deposit silicon on top of silicon, it becomes polycrystalline silicon, right? If you do it properly by epitaxy process, then it will be monocrystalline silicon. But we don't want to do that because this will be very thick and we cannot really, we don't want to slowly deposit it. That's the reason it becomes polycrystalline. But that is not an issue because we need a highly doped region, and polycrystalline we could also make very highly doped. So that will not be an issue.
yes, sir.
We are not intentionally doing polycrystalline. Polycrystalline silicon happens, right? Because when you deposit silicon on top of silicon, it becomes polycrystalline.
Yes.
So at the junction of polysilicon and silicon का जो emitter layer है, so there would be some defects. So that wouldn't cause any problem during the operation of the emitter.
So means there will not be defects. Yeah, there will be defects, but that is not an issue. There will be some interface, but that is not an issue. That is inside the emitter, right? So because you see, I mean, there will be some emitter also. There is some part in the emitter. Some part of the emitter is monocrystalline silicon, right? And the some part is polycrystalline, right? So when your junction is somewhere between emitter, right? And that junction is not very bad because this is silicon junction and equally doped, right? So right, there will be an interface, but that interface is not very bad interface, right? This is silicon interface still, right?
Yes.
Okay, so this is emitter crowding, and so another thing is uh, the breakdown, right? So basically, if you see, I mean, so I told you, right, operation of the bipolar junction transistor, most of the time we forward bias your emitter based junction. Forward bias means we will connect a positive voltage, and here I have negative voltage and Vc greater than Vb, right? So your collector based junction, this junction is reverse biased, right? And this junction is forward biased, right? Mostly, right? So right. So but what will happen is, so if so basically you see, this is, there is a reverse bias junction, right? As you go on increasing, let's say अभी VB को fix कर दिया, so let's say my VB is at 0.6 volt, right? And now I am increasing my VC, right? So because this junction is reverse bias, right? At some point, this junction will break, right? So we have also studied this the breakdown in PN junctions, right? So if you understand that, so if the PN junction is reverse biased, then you increase the reverse biased voltage across the junction. At some point, there will be avalanche multiplication and the junction will break, right? Similarly, this collector based junction is reverse biased, right? And so if I fix my base emitter junction, base emitter voltage be at point, let's say 0.6, 0.7 whatever voltage, then you go on increasing the collector voltage, right? At some point, this junction will break, right? And so on the reverse base junction, reverse bias junctions are more prone to breakdown voltage because this is reverse biased. Why reverse bias? Because when you apply reverse bias across a junction, the electric field in the reverse bias junction is higher than the electric field in the forward bias junction, right? Because the voltage drop across this junction will be VBI plus your VC here, right? VCB, right? But the voltage drop across this junction is VBI minus VBE because base emitter junction is forward bias. The voltage drop across this junction is reduced, right? But the voltage drop across this collector base junction has increased as you go on increasing the collector bias, right? That means the breakdown is more likely to happen in the collector base junction. That's why the reverse bias junction, right? But when you talk about the operation, basically, so I have two breakdown voltages in bipolar junction transistor. One is B breakdown voltage BVCBO, right? Uh, so you might have read about BVCBO so earlier. So this is the breakdown voltage of the collector base junction when the emitter is open, right? This is BVCBO. So this is nothing but your emitter is open. That means you are not applying any voltage to emitter. You are just applying reverse bias voltage across the collector base junction. Then you are seeing at what collector base junction your junction is breaking, right? So that is BVCBO. And another voltage which is important also BVCEO, that is the breakdown voltage. This is the uh, collector emitter breakdown voltage, right? When the base is open, right? Here the emitter is open, here the base is open. So I'll just here. So you see, this is my BVCBO, right? So I'll put my base to 0, and I'll go on increasing collector voltage. At some point, this will break, right? This is BVCBO, right? Because your emitter is open. Your emitter is open. You're not up, right? So BVCBO is nothing but the breakdown voltage of the collector base junction, right? Please tell me if this collector base junction is reverse biased. So we studied two kind of breakdown, right? So we studied about avalanche breakdown, we studied about Zener breakdown. What kind of breakdown will happen here in the collector base junction?
Avalanche.
Why avalanche?
Sir, because we are applying a very high electric field, so due to high electric field, we'll have
No,
avalanche
but
breakdown.
Zener also
because
use high
doping is low in
yeah,
collector.
because collector base, because both side, if you look at this base side and collector side, their doping is not very high, right? So since the doping is not very high, so if you look at a bipolar junction transistor, your emitter doping is highest, right? Then the base doping, then the collector doping, right? Base collector junction is not very heavily doped, right? Both sides are not very highly doped, right? That's the reason this junction is mostly avalanche breakdown, right? Mostly avalanche, no Zener breakdown, right? So mostly avalanche breakdown, right? Similarly, so if your base is open, right? Your common emitter configuration, let's say your base is open, right? You will go on increasing collector voltage. At some point, this we call means very high current will flow. So see, basically, this is again a diode structure NPN, but your base is open. So here base is open, right? So this is my VC. As you go on increasing VC, at some point your current will be very high, right? Right. That is so since your base is open here, so we call it breakdown voltage between collector and emitter because you're applying voltage across collector and emitter when the base is open, right? 0, right? BVCO. But here there is no junction breakdown because you see there is no junction between collector and emitter, right? There are two junctions between, if you look at collector and emitter, there are two junctions between collector and emitter. When you're talking about collector emitter breakdown, that means both the junctions are breaking, right? But when you're talking about collector base breakdown, BBCBO, that means one junction is breaking, right? Okay, we will discuss about these two things, BBCBO and BBCO, because they are very important. And why they are important? Because you see, this is the common base, right? So output characteristic in the common base configuration, right? Output characteristic in the common base configuration, right? You see, your common base configuration, when base is common, right? So your output current is collector current, your input voltage is VCB, right? So if you see your at some point, if you go, because this is VCB here in the your VCB here in the y-axis, as you go on increasing VCB, at some voltage this will break, right? Because the collector current will be very high, right? Avalanche multiplexing will happen and junction will break. So this is my BBCBO, right? So what is the significance of BBCBO? Let's say you are operating your bipolar junction transistor uh, in common base configuration, right? So BBCBO will tell you what is the maximum voltage, output voltage you could give to your bipolar junction transistor, right? See, output power is nothing but the output voltage and the output current, right? So so if you're designing amplifier where you want to have output voltage, means output power or output voltage needs to be very high, right? So this will just tell you what is the maximum output voltage you could give, right? BVCBO, right? Higher the BVCBO, higher the maximum voltage you could apply, right? Okay, when I'm talking about maximum voltage, so basically your in this case your emitter is common base configuration, so your base is common here, right? So voltage that you're applying across, I give some VCC here, right? So, and you give some forward bias because this junction, this is emitter, this junction needs to be forward bias. So let's say emitter is open. So emitter is open means, I mean, I'm not giving any voltage here. So what is the maximum? Because this is my collector, so I give VCC to the collector in the normal circuit operation. I give VCC to collector. So this BBCO will tell you what is the maximum VCC that you could give, right? What is the maximum voltage you could give, right? So, so if I'm telling, okay, this transistor is operating at 3 volt, or transistor is operating at 5 volt, or transistor is operating at 7 volt, I'm talking about VCC, right? So this VCC will determined by the BBCB. If you need 7 volt operation, if I need 7 volt here, let's say I need to give a volt VCC of 7 volt, that means your BBCBO should be more than 7 volt, right? So your BBCBO should be more than 7 volt, or at least it should be 1.5 to 2 times, right? When you're talking about 7 volt of operation voltage, your BBCBO should be around 12 to 13 volt, right? Similarly, in the common emitter configuration, when you're operating in common emitter configuration, your output voltage is VCE, right? Because your emitter is common. In this case, your common emitter configuration, right? You're giving your input voltage, so your VCC is here, so output voltage is VCE, right? So here, so you see your BBCO will tell you what is the maximum VCC could give. What is the, because your let's say your emitter is grounded, right? So if you see, if you remember the amplifier circuits or any circuit operating means utilizing bipolar junction transistor, right? So here the output voltage is VCE, right? And you see, if you want to increase VCC, right, at some point your junction will break, right? If you go on increasing VCE, or some point junction will break, right? So the transistor will have very high current, right? So this is the BBCO. So for a common emitter configuration of common emitter mode of operation, your VCC that you could, VCC max, right, or VCE max that you could apply, VCE max, should be less than BVCO, right? So that's the significance of BVCO, right? And see, and you could, I mean, you could clearly see your BVCBO is much higher than BVCO. BVCBO is higher than BVCO, right? And we will see how, why, right? So and but when you are, let's say you want to operate your bipolar junction transistor at 5 volt, right? So you have to make sure your, let's say your VCC is 5 volt. That means your BVCO should be greater than 5 volt, right? At least, right? And anyway, BVCBO will be, anyway, if BVCO is greater than 5 volt, BVCBO will also be greater than 5 volt, right? That will be by default, right? If you design your transistor in such a that your BVCO is more than 5 volt, then your automatically your BVCBO will be more than 5 volt. That will be because your BVCBO is always more than BVCO, right? Okay, so let's understand, right? Oh, already we have 6 minutes past 12. Okay, so let me stop here today.